Hello friends and welcome back to my channel AI with Grounding. This is the first step in the series RAG from Retrieval to Grounded Reasoning Roadmap. Today's video is on keyword retrieval or keyword search. We start this series with extremely basic architecture. At this stage, there is no AI, no embedding, no LLMs, no GPUs were harmed in building these retrieval engine. This is just traditional information retrieval, the kind of search engine used for decades. If you ever wondered what systems look like before modern RAG, this is it. The idea is simple. We convert every movie into a text document that contains important attributes. Then we build a keyword search over those documents. When a user asks a question, we compare and find cosine similarity in the words in the query with the words in each movie document and rank the most similar ones. No reasoning, no understanding, just word overlap statistics. Now let's see how keyword retrieval is actually built in code. Because retrieval is not complex, it is just a clean pipeline. First, we load movie datasets, basics, ratings, principles, names. These are raw tables, not searchable yet. Next, we clean and combine them. We filter the records. We aggregate useful attributes and create one canonical, standardized, searchable document per movie. This is the most important step. Now comes the vector engine. We use TF-IDF. This converts movie text into keyword importance numbers. The result is a sparse matrix, meaning most words are 0 for most of the movies. Then comes search. User query goes through same vector transformation. Then we compute cosine similarity. After that, we sort the result. And boom, now we have a working keyword retrieval engine. No AI magic yet, just smart text math. Let's quickly see what tools we are using. For data handling, pandas. It helps us clean, joins and reshape movie files. For feature extraction, TF-IDF vectorizer. It converts text into numerical keyword signals. Rare words get more importance, common words get less. And for measuring closeness, we use cosine similarity. It tells us how similar a search query is to each movie document. That's the full engine. Simple, classic, but extremely powerful. And this becomes the first building block of RAG because retrieval always comes before generation. Quick detail about movie dataset and its data model. Each dataset for movie metadata, rating, cast, crew, and actor details. We will filter dataset only to select movies that also top 20,000 by votes because nobody wants search results from films watched by the director and his own cousins. Okay, let's see some sample records of each raw file very quickly. First one is the master raw file for movie titles. Each movie name has an ID starting with TT. Second one is the rating of movie title. Third one contains name of people. Each person has an ID starting with NM. Last one is people in movie association. Movie titles with TT and person name with NM. Now we flatten the structure into searchable text. Each movie becomes one text paragraph. Structured data become unstructured. My fellow data modelers and data architects don't feel uncomfortable. I know from a data model point of view, this feels slightly illegal, but a retrieval point of view, trust me, this works beautifully. Now we reach the brain of keyword retrieval, TF-IDF. Yes, the name sounds like a rejected Wi-Fi password, but the idea is actually very simple. TF means term frequency. How many times does a word appear inside one movie's description? If a word matrix appear again and again, that movie is probably matrixy. Now comes IDF, inverse document frequency. This checks how rare that word is across all the movies. Because if every movie says movie, then the movie words tell absolutely nothing. But if only a few movies like Matrix, then we can getting somewhere. So TF-IDF is basically asking two questions. Does this movie really care about this word? And does the rest of the world care less? If both are true, boom, high importance. In retrieval, not all words are born equal. Some words are just background noise. For example, the word movie. Very common, very generic, very useless. Now takes a word interstellar. Much rare, much more dramatic, much more helpful for search. And then we have a word like sci-fi. Somewhere in the middle. Not super rare, not super common. TD-IDF acts like a spotlight operator. Common words stay in the dark. Specific words get full cinematic lighting. This colorful grid is our TF-IDF matrix. Each row is a movie, each column is a word. and each number tells us how important that word is for that movie. This image results in a perfect example of a sparse matrix. Most values are 0, which is great because most movies do not talk about most words. Imagine if every movie mentioned space, mafia, and dinosaurs. The cinema would be very confusing, isn't it? So, this matrix is sparse but extremely informative. And here is the key transformation. We just converted text into vectors. One movie, one vector. Which means now we can finally start doing math on meaning. And that is where retrieval becomes powerful. Now comes the final step, ranking. User types a query. First, we convert that query into a TF-IDF vector. So now the query speaks the same numeric language as movies. Next, we compare this query vector with every single movie vector. Yes, every one. This is basically a giant speed dating event for vectors. And for compatibility test, we use our old friend cosine similarity. Now don't panic at the math. Cosine similarity is simply measuring how aligned two vectors are. Not their size, not their length, just their direction. If two vectors point in the same direction, similarity is close to 1. If they point in totally different direction, similarity moves towards 0. Let's come back to our pipeline. We are asking, does this movie talk about the same important words as the query? If yes, high score. If not, sorry, better luck next ranking. Finally, we sort all movies from higher similarity to lowest. And just like that, we have search results, no neural networks, no embeddings, no black box magic. Now, let's see the code. Okay, let's start by importing some of the important libraries. As we discussed earlier, first one is Panda, the other one is TF-IDF vectorizer, and third one is cosine similarity from scikit-learn. Next step is to load the movie data from the raw files into the data frames. For that, we have defined a function, load IMDb data, and then we are loading the basics, rating, principles, and names from the raw data into the data frames. Now this is the backbone of our code. We are building the text corpus here. Here we are giving limit of 20,000 movies, and per movie we want to capture only 6 cast members. The first step is to use the load IMDb data function and load these data frames. Next step is to build the movie base first by merging the movie basics with the ratings and filtering only the movie's title type. All this merging is happening on the tconst, which is the ID column of the title of the raw data. Okay. Next step is to clean the data. Here we are replacing the invalid years value \n with none. And we are converting the start year into numbers. In the next step, we are choosing most useful movies first from the vote so that our subset is strong. Here we are converting votes and ratings into numeric values. We are filled the missing values with 0. Then we are sorting the movies by number of votes with the most popular one first. We are keeping only the top 20,000 movies. Limit underscore movies is a parameter which we have set up as 20,000. Next step is to filter principles to only related to movies. We'll get the IDs of selected movies and then we'll filter the principal only those movies. Next step is to keep only actors, actresses and directors. Then we'll get the IDs of people involved in selected movies and then filter the name only for those movies. While fetching the name, we'll get the ID of people involved in selected movies. We'll filter the names of only those people. In next step, we'll merge the principal with names to replace IDs with actual names. Now we'll start building the cast list. First thing is we'll do for actor and actresses, and we'll do a comma separated top n cast members. So the list will look like actor 1, actor 2, actor 3. To get the director, we'll group the director by movie and then we'll take the first director and we'll store in a new column as director. In the next step, we'll add the cast and director info back into the movie data frame. Finally, the most important step, we'll build the canonical doc by combining all the information which we have derived so far into one single doc text summary column. Next step is we are building the keyword index. So for that, we'll use TF-IDF tokenizer and we'll ignore the common English words. We'll filter on the movie description doc, and at the end, we will return both the vectorizer and the matrix of numbers. Okay, next function we are defining is the keyword search. Here, first we'll convert the query into a vector, then we'll compare that with all the movies using cosine similarity. Then we'll sort the result and pick the top k results. Then we will return the details of those movies. Now we are introducing our 4 questions and we'll set the path. Let's start running those functions which we have built. First thing is we'll build the text corpus. This step will take a bit of time. I'll take a pause here and I'll come back once this step is over. Okay, so the corpus has built. Now we'll build the keyword index. Okay, now moment of truth. Let's run all our questions one by one and see how the keyword retrieval is working. Okay, let's analyze these results and see what is happening. In the first question, interstellar is fine, but if we see the other result, they are not accurate. And it seems like the word like has been favored. So all the movies with like are coming here. So the result is not so good, which is expected. For next question, top rated sci-fi after 2010. But the results are not so good. All the results are neither sci-fi nor after 2010. So the keyword retrieval is not able to filter the records at all. For the third question, the answer is Shutter Island, Inception is okay, but remaining are not so good. But the still result is average, not so bad. For the last question, it is able to figure out all the relevant movies, but it is not able to figure out the relationship. Okay, let's come to the score and evaluate the result. For question 1, which tests relevance, the system doesn't understand the meaning. It only matches exact word. Like in this example, it was very much inclined towards the word like. If a movie is similar in theme but doesn't share those keywords, it might never appear. For question 2, keyword search will again match words like sci-fi and 2010, but it doesn't really understand filter logic. It just rank document with similar terms. For question 3, keyword search will simply match the name Leonardo DiCaprio inside the cast field. There is no understanding of time range or actor relationship. Question 4 requires reasoning across two movies and their cast list. Keyword search has no concept of relationship, so it will usually fail or return random results. Let's see the goods of this method. It is fast, deterministic, easy to implement, works for direct name matching, and good for lexical searches. But this method has no semantic understanding, no reasoning, no relationship awareness, weak with synonyms, cannot apply logic filters cleanly. Intellectual sci-fi make you think, cerebral sci-fi make you think and stare at the ceiling wall later. Current method not able to differentiate this vibe. Today we took our first step and we set the base. Results are not so good, but we are keep improving in next steps. Bye for now, and as always, explore AI but with grounding. Thanks for your time.